In this video, we're going to do some more complicated practice problems using the integration by parts technique and formula. So first question is, using this integration by parts, find the integral of 3x plus 4 times sine of 2x dx. This is of the form a polynomial times a trig function, and we learned in the previous video that I'm going to let u equal the polynomial function, and I'm going to let dv be the trig function. So this sine of 2x is going to be our trig function. We're going to let that be our dv. I should say with the dx included, as I'm going to take the antiderivative. And the polynomial function, this 3x plus 4, is going to be our u. Now these are much more complicated functions to deal with than the previous video, but again, that's the goal of this practice video. So we're going to take the derivative of u to find du, and that's going to give us a 3. We're going to have a dx come along for the ride. And here we're going to take the antiderivative, which is the integral of sine of 2x dx, and we have a formula for that. That's going to give us a 1/2 cosine of 2x with a negative, because the derivative of cosine is negative sine, so the derivative of negative cosine will be positive sine. All right, and that takes a little bit of work getting used to. This is a formula that we have, or if you're not comfortable with that formula, you could do the integration by substitution method with u equal to 2x in that little integral. Once we have this, then I'm going to rewrite my original integral of 3x plus 4 times sine of 2x dx is going to be equal to taking the u times the v, so that's going to be 3x plus 4 times negative 1/2 cosine of 2x. And I'm going to subtract off that bottom line. So that's going to be minus the integral of negative 3/2, taking the 3 times the 1/2, cosine of 2x dx. And that is a doable integral. It's going to be very similar to the integral that we did before, and we have a formula to do that. So our answer here is going to be, the first chunk just comes along for the ride. There's no integral attached to it. We're done with that. That's going to be 3x plus 4 times the negative 1/2 cosine of 2x. And here we're going to have minus this integral, which is going to be negative 3/2 times 1/2 positive sine of 2x. All of this plus c. So then simplifying, maybe we have 3x plus 4 times this negative 1/2 cosine of 2x. And here we're going to have plus 3/4 sine of 2x plus c. This problem is a little bit difficult for a number of reasons. One, the functions that we're dealing with are just more difficult, which means that the antiderivative, especially for that sine of 2x, has some getting used to. And then, of course, because of that, the second antiderivative we do is easier to deal with, but it's still a little bit difficult. And the constants we have floating around can make things more difficult too. Let's look at another practice problem, and that is going to be the integral of 3x squared e to the 4x. This is of our form a polynomial times an exponential function, and we learned that if we let the polynomial function 3x squared be u, and the exponential function with that dx be our dv, that's going to be something that's going to work here. So we're going to take the derivative on the left-hand side to get the du, and the derivative there is 6x with the dx coming along for the ride. And here we're going to take the antiderivative, and that's going to give us a 1/4 e to the 4x. And this is the integral of e to the 4x dx. And there's a formula that we have that tells us it's going to be 1 over that constant times x, so 1/4, and the rest of it is the same. So rewriting this, we have our original integral is going to be equal to this diagonal, u times v, that's going to be a 3/4, the 3 times the 1/4, x squared e to the 4x. And I'm going to subtract off minus 6/4 x e to the 4x dx. And I want to make very clear that this is not a straightforward integral. The fact that there's an x there is difficult, but we can do this integral using integration by parts one more time. And this is going to be a common practice for integration by parts, is doing integration by parts more than once. In this case, doing it 2 times in a row. What we said is that the purpose of an integration technique is to take an integral and make it easier to do. And that's, we've taken this 3x squared e to the 4x, and we've brought it down to a x e to the 4x times a constant. And we're going to do it one more time to bring it down to just an e to the 4x. So we're going to see that on the next page. So this is what we had written down, except that I have simplified the 6/4 to give us a 3/2. Everything else is the same. And we're going to do integration by parts on just this integral right here. So this is of the form a polynomial times an exponential. We're going to let our exponential function times dx be our dv. And we're going to let our polynomial 3/2 x be our u. We're going to take the derivative. That's going to give us 3/2 with a dx attached to it. And here we're going to take the antiderivative. That is the antiderivative of just e to the 4x dx, which again is going to be 1/4 e to the 4x, just as it was in the previous problem, or the previous application of integration by parts. So now we have, writing everything down, our original integral is going to be equal to what we found from the first integration by parts, 3/4 x squared e to the 4x, minus, and then everything here is going to be from our new integration by parts. We have u times v, which is going to be 3/2 times 1/4. That's going to be 3/8 x e to the 4x. And we're going to subtract off the integral. 3/2 times 1/4 is going to be, again, 3/8 e to the 4x dx. And once again, we've made this integral easier to do. Now it's a straightforward antiderivative, and we can finish this problem. So we have 3/4 x squared e to the 4x. This is from the first application of integration by parts. Minus, and I'm just going to keep everything in parentheses right now, not to confuse our signs, 3/8 x e to the 4x. And then this integral is going to be minus 3/8 times 1/4 e to the 4x. This is the antiderivative we've done 3 times now in this problem, plus a c at the end. Maybe one more step here is that we could distribute that negative. We have a 3/4 x squared e to the 4x minus 3/8 x e to the 4x. And here we're going to have a plus because we have this negative distributing there, plus 3/32 e to the 4x plus c. And although all those terms have e to the 4x, they all have to be separate terms there. Dealing with integration by parts multiple times can be a long problem, but as long as we are careful with where stuff's coming from, we're careful with our work, we can track the negatives and the signs and the distribution that we need to do. So let's see another application. In this case, we're going to look at the square root problem as well as having some bounds on our integral, a definite integral. So here we have a polynomial times a square root, and we said that in this case we are going to have our polynomial function, in this case x, as our u, and we're going to have our square root be our dv. Now this only works for a few square root functions because the antiderivative of a square root by itself can be a difficult thing to do. But in this case it's going to work, so let's see it. This is going to be, the derivative here is just a 1, and a dx comes along for the ride from the derivative. Then we have here this antiderivative is going to be, again, the antiderivative of square root of x plus 1 dx, which is the same thing as x plus 1 to the 1/2 power. You may think that's a straightforward antiderivative. If not, then I urge you to do this substitution. U equals x plus 1, and you will see du dx is equal to 1, du equals dx, and you can rewrite this as u to the 1/2 du. In either case, the antiderivative is going to be a 2/3 x plus 1 to the 3/2 power. You could do that with the u, increase power by 1, and then divide by it, or just have the x plus 1 in your mind. So here we're going to have our original integral from 0 to 1, x square root of x plus 1 dx. It's going to be equal to u times v, that is 2/3 x times x plus 1 to the 3/2, evaluated from 0 to 1, minus the du times v, and that's going to be 2/3 times 1, which is 2/3, x plus 1 to the 3/2 dx. And this is from 0 to 1. Don't forget the bounds on the integral. Writing this down, I'm going to evaluate everything at the very end. We're going to have 2/3 x times x plus 1 to the 3/2 minus the antiderivative here is going to be 2/3 times 2/5 x plus 1 to the 5/2. All of this evaluated from 0 to 1. Now we plug everything in. We're going to have 2/3 1 times 1 plus 1 to the 3/2 minus, we're going to write this as 4/15, 2/3 times 2/5, 1 plus 1 to the 5 halves, minus plugging in 0. Be careful that plugging in 0 doesn't always give you a 0, and in this case, there's going to be something left over. But we'll just write it all the way out. This is going to be 4/15, 0 plus 1 to the 5 halves. And then we're going to call this just our answer right here. We could go through the process and simplify if we wanted to. These square root problems are not going to be very common, but they do pop up occasionally, and this process will work for simple square root problems. There's other ways to do them. Integration techniques are not unique. You could use different ones to do it, but this is one way to do it. So let's do one final problem in this video, and that is use integration by parts to find the integral of x to the 9th natural log of x dx. This is of the form a polynomial times a logarithm. And in this case, we said that our polynomial, in this case, the x to the 9th dx, is going to be our dv. And our logarithm is always going to be u for these problems because we don't know how to find the antiderivative of it easy. So if we take the derivative of natural log, we're left with 1 over x times dx. And if we take the antiderivative here, that's going to give us a 1/10 x to the 10th power, just using the reverse power rule. So here we have the integral x to the 9th natural log of x dx. Our original integral is going to be equal to u times v, 1/10 x to the 10th natural log of x, minus the integral of 1/10 times 1 over x times x to the 10th dx, which looks terrible. However, we can do some simplifying and rewrite this as, sorry, let me rewrite the first part, 1/10 x to the 10th natural log of x minus the integral of 1/10, this is just going to be x to the 9th dx. And that's a straightforward integral. This will give us 1/10 x to the 10th natural log of x minus 1/10 times 1/10 is going to be 1/100th x to the 10th plus c. As is the case with integration by substitution, integration by parts is very confusing at the beginning. Dealing with the u's and the v's and the du, dv, dx, there's a lot to do. The formula can be tricky at the beginning. However, with practice, the formula becomes easier, and it really does just boil down to, can you correctly identify the u and the dv?